Pass-through distillation. Part 2. Temperatures and pressures.
Distillation is a versatile technique for separating materials, but many applications are complicated by temperature concerns, necessitating costly workarounds. In ethanol plants, thin stillage evaporators and reboilers foul at temperatures greater than 80 C. As low as 70 C, oil and oil additives may be damaged in oil recovery stills. Above 60 C, enzymes may be denatured. Delicate aromas and flavors are affected in juice concentrators around 50 C. In wine dealcoholizing, temperatures above 40 C will compromise flavor. And in industrial fermentation plants, yeast and other bugs die at temperatures greater than 30 C. But large-scale industrial distillations are rarely carried out below 70 C, giving rise to a lot of cleanup, redundant equipment, and lost opportunity. Why can't distillations be carried out economically at lower temperatures? The problem can be traced to two basic causes. First, condensers are coupled to evaporators. They operate at the same pressure, and so their temperatures cannot be controlled independently. Secondly, condensers are almost universally cooled by a plant cooling water system based on evaporative cooling towers, and these deliver water in summertime at 30 C. With 30 C as the cooling water inlet temperature, the condensing temperature will be at least 45 to 50 degrees C, and the minimum boiling temperature somewhere around 70 C. But as we have noted, the temperature sensitivities can be as low as 30 C. Refrigerated condensers can move the temperatures down to a safe level, and these are applied in industries like pharmaceuticals, where production volumes are small and the product selling price is high. But refrigerated condensers are too expensive to operate for large-scale commodity producers. Refrigeration addresses the limitation imposed by plant cooling water temperature. But remember, we observed that another cause of temperature problems is coupling between evaporator and condenser. If they could be decoupled and operated at different pressures and temperatures, could low temperature distillation be achieved? In science class, we learned that a vacuum pump can cause a glass of water to boil at room temperature. The vacuum pump removes air from the bell jar, reducing the pressure. When boiling starts, the water vapors generated are exhausted through the vacuum pump and discharged into the air. To turn this into a distillation operation, a condenser could be connected to the vacuum pump discharge. Ordinary cooling water would be adequate to condense the water vapors. An arrangement like this might be useful at lab scale, but is rarely, if ever, used at industrial scale. The vacuum pumps would be enormous and incur unacceptable energy costs. But at least this demonstrates that very low temperature distillation is possible when the condenser is decoupled from the evaporator. Pass-through distillation is another way that decoupling may be achieved. The main evaporator and the absorber operate at very low pressure. For instance, water boils at around 30 C at an absolute pressure of 30 torr, or 1/25th of an atmosphere. The vapors entering the absorber are not condensed but absorbed, while air and other non-absorbable components are carried through the vacuum pump. The desorber may operate at much higher temperature and pressure. It might operate as an atmospheric still, with its condenser cooled by ordinary plant cooling water. So pass-through distillation by decoupling evaporator and condenser makes possible economic low-temperature distillation. The commercial consequences could be substantial. For example, one of the costliest ingredients in the making of cellulosic ethanol is the enzyme package. Enzymes are denatured by conventional distillation and could, at least in theory, be recycled after a low-temperature distillation. Most plant people would agree that low temperature distillation is desirable as long as it is economic. But how can economy be served when product is boiled once in the main evaporator and a second time in the desorber? In Part 3, we will examine the energy flows in a pass-through distillation system that uses half the energy of a conventional still.